Michaela. I would like to start with pointing out that I very much share your feelings of being greatly honored to stand here in a symposium where the two other speakers are Katalin and Gera. You are role models for me, I guess for all of us, and provide us a great deal of motivation, I guess not just myself, but to our whole team to do something that somehow either benefits from what you have done in the future. Gera, we of course will heavily use your Nobel Prize winning work on chirp pulse amplification, or doing something, I wouldn't say comparable, because I don't think we have the chance for that, dear Katalin, but at least something that goes in the same direction, to do something useful for everyone on this planet. The eternal truth of Max Planck, the more delicate the details are by which we can follow nature on any path, the richer and the more lasting will the gains be that we can draw from this perception. In my example, the delicate details will be electronic motions in tiniest dimensions in space and time, and one of the hopefully lasting gains will be the cost-effective probing of human health. More specifically, I'll address how the new discipline of attosecond physics opens the door to the world of subatomic motions, of tiny particles called electrons, which can now be initiated, controlled, and captured by light with the tools and techniques of the new discipline, attosecond physics. The interaction of electrons with light plays a pivotal role in advancing existing and spawning new technologies. The more precisely we are able to control electrons and light, the richer and the more lasting the gains will be that we can draw from this ability. In what follows, I will focus on a specific example that is closest to my heart, the subatomic motion of electrons in organic molecules, which provide valuable information about our health state and hold promise for contributing to shaping the future of preventive healthcare. It is a grand goal that we pursue with our dream teams in Munich, Budapest, and here in Szeged. Grand goals can always be best defined by grand questions, and I will share with you our grand questions in the concluding part of my talk. After a brief recap of subatomic motions, we shall quickly move ahead to address how they can contribute to preserving human health when happening in a controlled and observable manner in molecules. But before we immerse in the world of electrons and light waves, a brief historical review is due, just to pay tribute to all those the shoulders of whom we are standing, on the shoulders of giants. On the dawn of the 20th century, Joseph Thomson's experiments provided compelling evidence for the existence of electrons as subatomic particles with an electric charge opposite to the one carried by the remaining, much more massive, much more heavy part of the atom. It was Ernest Rutherford whose experiments revealed that this remaining, much more massive part is concentrated in a tiny, tiny volume, some 10,000 times smaller in diameter as compared to the size of an atom. It's amazing that we knew it at that time already, more than 100 years ago. More than 100 years ago, that the core of the atom is 10,000 times smaller than the size of the atom. It's amazing that we knew how big the atom is, and it's amazing that we knew how small its core is. And that's the latter part came about by Rutherford's experiments. And it was Niels Bohr who made the first rigorous attempt to explain how it is that the atom is that much bigger than its core. Why are the electrons that far away from this tiny little core? Just imagine they attract each other. The electrons have negative charge. The nucleus has a positive charge. They attract each other. So why aren't the electrons just sucked into the nucleus and the whole atom is just as small as its nucleus? They are all together. Why not? Why not? Niels Bohr was the first to make a rigorous attempt to explain. He said that, well, the electrons are orbiting the nucleus just as planets are orbiting the sun on some well-defined microscopic orbits. But there was a problem with this. We knew from previous studies, previous discoveries by Maxwell, Faraday, and all the others, the charged particles, when they are accelerated, are radiating light, radiating electromagnetic radiation. They lose energy. So if the electrons are orbiting around the nucleus, they are constantly accelerated because they are on a curved trajectory. So they should radiate energy away. If they radiate energy away, they lose energy all the time. If they are losing energy, they should spiral into the atomic core, and tuck, they are sitting in the core, right? So why it's not happening? Bohr tried to solve this problem by postulating that the electrons, this basically have to have a certain angular momentum, and this was a postulate nobody understood. And this way, basically, he could explain some spectroscopic observations, but nobody was really happy about this. The really satisfying explanation came about with the birth of quantum physics. Louis de Broglie from France proposed an answer which holds true until today. He postulated it may be due to the wave nature of the electron, and, equally importantly, a linear relationship between its wave number and momentum. Indeed, to compress this wave, if we accept this notion that the electron is a wave, if we want to compress this wave to an ever smaller size, to eventually reach the size just of the nucleus, this would mean that its wavelength must get smaller and smaller, but due to the linear relationship between wavelength and momentum, its momentum would become larger and larger. And a particle with a larger and larger momentum cannot possibly fit in a smaller and smaller pace. It needs space to move around with a higher and higher speed, right? So even without Schrödinger equation and all the other rigorous theoretical foundations of quantum mechanics, already this very postulate of de Broglie, electron is a wave, with a wave momentum, with a wave number of this wave being proportional to the momentum of the electron as a particle, basically explained why the atom with its electron around the nucleus is much bigger than the nucleus. Without any theory. Isn't it just ingenious? Isn't it just ingenious? It was a doctoral thesis, by the way. Quite a nice one, isn't it? With which one earns a Nobel Prize. Obviously, Schrödinger was that much impressed by this that Schrödinger just couldn't wait to move ahead even without an experimental proof of de Broglie's hypothesis, because the actual wave nature of the electron was experimentally proven just years later, which also earned to the experimentalist the Nobel Prize just a few years later. But it came up quite a few years later. Schrödinger didn't wait until then. He was so much fascinated by this notion that the electron might be a wave that just a year later, he came up with his famous equation, born in Vienna, the equation. It was Max Born who actually postulated that the modulus squared of the wave function, of Schrödinger's wave function, gives the probability with which we can find an electron at different locations. You see this modulus squared of the wave function depicted just on the right-hand side of the slide for the simplest atom in our universe, for the hydrogen atom consisting of one proton, this is the nucleus, positively charged, and one electron around which is negatively charged. And that one electron has this wave function, actually the amplitude squared of the wave function, and basically where this green cloud is brighter, this means that actually this modulus squared is bigger, and we will find the electron in those regions of space with higher probability as compared to regions where this gets weaker and weaker and eventually dark. So you see from this what is the size of the hydrogen atom. Basically this comes from the solution of the Schrödinger equation, and this is right, experimentally of course verified all these things. Meanwhile, so far so good. But you remember the title of my talk is Subatomic Motions. Where is motion here? Nowhere, right? There's no motion. I mean, everything stands still. How to actually create motion in the subatomic world? Well, the Schrödinger equation gave the answer to that as well as to anything else that you may ask in the context of processes in the microscopic world. We need to excite the electron from this ground state where there is no motion into some excited state. Like here, the simplest excitation from the 1s to 2p state by the absorption of a photon of corresponding energy, and all of a sudden, in the so-called superposition state that is created by that way, we see that motion is there. Basically, this electron cloud, the probability distribution of the electron starts moving. And that's exactly what microscopic motion, subatomic motion is about. This is the closest analogy to motion in the macroscopic world. Motion in the macroscopic world we can simply imagine. We are just moving, I'm moving aside and I'm moving, right, as a macroscopic object. In a microscopic world, we cannot track the trajectory of microscopic particles, not because we are not skilled enough experimentalists, but nature doesn't allow us to do. Nature allows us to say something only about the change of this probability distribution of particles like the electron. That's what we see here for the simplest case. So this was known in 1925, actually almost 100 years ago. Just next year we will have the 100-year anniversary of the birth of quantum physics, with quite a few big events coming up. And well, 75 years later, after 75 years after this insight into subatomic motions emerged in the birth of, with the birth of quantum mechanics, it could eventually be captured in real time by the experiments performed in Vienna and almost the same time in Paris. Key tools for this breakthrough have been intense near-infrared laser pulses carrying a substantial fraction of their energy in a single oscillation cycle, demonstrated in Vienna in the mid-90s, together with colleagues from Budapest and Milano, by drawing, well, we are standing on the shoulders of giants, I told you already, by drawing on the Nobel Prize-winning concept of chirp pulse amplification of Gerard Mourou and Donna Strickland. I'll briefly refer to these pulses as single-cycle laser pulses or waveforms in the remainder of my talk, exposing noble atoms, noble gas atoms, to such a single-cycle laser field almost naturally creates isolated pulses of attosecond light, almost naturally creates them, which together with the controlled force that the electric field of this single cycle light exerts on electrons, which is varying on an attosecond scale. With this controlled attosecond varying electric force constitute the basic tools for real-time observation and control of electron light phenomena. To quote Eva Olsson, the chair of the Nobel Committee for Physics, we can now open the door to the world of electrons. Attosecond physics gives us the opportunity to understand mechanisms that are governed by electrons. The next step will be utilizing them. So far, so good. However, just look at this, how complex this apparatus is to do actually this attosecond photography and capturing the motion of electrons. It's tremendously complex, tremendously complex. In order to be able to tackle real-world challenges, attosecond technology must become much simpler and more powerful. And exactly this was recently enabled by single-cycle light, which allowed us to inject carriers into the conduction band of an insulator, turning this insulator into a conductor within less than 1 femtosecond in this way, and allowing thereby sampling of the electric field of visible light. Many of you know the concept of an oscilloscope with which we can measure the temporally varying voltage of an electric signal up to microwave frequencies, up to, meanwhile, around 100 gigahertz, 100 billion oscillations per second. These light waves oscillate another something like 10 to 100,000 times faster, more frequently as compared to those microwaves, and we can capture them now with a simply solid-state instrument without the need for any vacuum system. This is something simply and handy. And we can realize basically an oscilloscope that captures the electric field of visible light, as demonstrated here, actually even more than that. Meanwhile, just very recently, these are unpublished results, Amelie Heinzerling and Nick Karpowitz extended this capability to frequencies up to beyond 1.5 petahertz in the region of deep ultraviolet light. So you see here that the half oscillation period of such a deep UV light at wavelength around 200 nanometers lasts about half a femtosecond, 500 attoseconds. So we need a resolution, temporal resolution, obviously better than this, couple of hundred attoseconds actually. So light field sampling now provides a new probe for subatomic motions without the need for complex vacuum systems. Simple, compact probe, just tabletop probe. The electric field of light from the infrared to the ultraviolet, which will be helpful for advancing electronics from the current gigahertz processing speed towards terahertz and potentially even petahertz processing speed, some 100,000 times faster processors than we have today, and probing the molecular world. And that's what I'd like to focus on in the remainder of my talk, by the use of actually infrared excitation. But I would like to point out that this is not the end of the road. I firmly believe that we will be able to extend the technique, and it will be worthwhile to extend the technique that I'm going to share with you in a moment from the infrared to the ultraviolet. And as I just showed you, we have now the technological capability of doing this. We just need to do that. But the rest of my talk will focus on what we do with infrared light, which is oscillating slightly slower than visible light. In conventional infrared spectroscopy, continuous wave infrared light excites molecular vibrations causing dipole oscillations of the electron cloud. Again, this green cloud, that's what I showed you before. These are again electrons, right? This is the electron distribution around the nuclei. And as you saw, this infrared light can bring certain atoms bound with this chemical bond. The chemical bond is this electron cloud, right? Can bring into oscillations. These radiate also infrared light, and this is actually the orange colored wave, which is usually much weaker than the excitation wave, and notably it is of opposite phase as compared to the excitation. As you see, as the excitation is oscillating upwards, the wave that is radiated by this vibrating molecule is oscillating downwards. This results in a destructive interference between the two, and at the output, if we put an infrared spectrometer and analyze the frequency components of this transmitted infrared light, then at this very frequency, we will see a small dip. Basically, this is the result of a negative interference between the input light, which is basically this whole distribution. It's a broadband infrared excitation, and at the very frequency where this very bond is oscillating, another infrared wave is generated from the molecule, which is opposite in phase to the excitation wave, and the sum of the two, which we measure in the instrument, basically is something that has a decreased amplitude, and this is the dip. And this is what conventional infrared spectroscopy does. It's beautiful, has been done for decades. There is one big problem with that this excitation that has this broad distribution, the incoming light, is always tainted with some noise. So it has never a perfectly constant amplitude, but it's always noisy a little bit. You can imagine this noisiness means that actually this envelope here in the spectral distribution, these are the individual amplitudes actually at the frequency components or wavelength components shown here. They are also uncertain in a little bit. They are all noisy, right? So obviously the smallest dip that we can possibly see is limited by this noise, right? So if the noise is that big, then any dip that is smaller than this noise will not be visible. So we cannot measure, right? So this noise in the excitation will impose a firm limit on the sensitivity of the technique. Due to this noise, below a certain level, we just will not see if anything changes in the sample we are looking at, right? So, the infrared waves that emerge from this subatomic charge displacement in molecules carry information about its atomic composition and structure, about the atomic composition and structure of these molecules. And the overall molecular signal that we get out of the sample therefore probes the global molecular landscape of the sample under scrutiny, rather than measuring actually a concentration of a subset of molecular constituents, such as for instance, in mass spectrometry. But this, as I just mentioned, this type of continuous wave infrared spectroscopy suffers from low sensitivity due to the weak molecular signals superimposed on a noisy excitation. In our new approach, we separate the weak molecular signal from the excitation noise by a sudden, impulsive excitation. Just imagine a tuning fork of a musician who hits its tuning fork with a small hammer, and then listen for tuning his instrument. Just imagine that these molecules play the role of the tuning fork. They are hidden. They are being hit by a very short pulse. This is the hammer. And then left alone. Just as the musician afterwards can listen very nicely the acoustic vibrations of the tuning fork, if you all are supposed to be very quiet, right? If you would be noisy, he wouldn't hear it, couldn't tune his instrument, right? In the same way, as the musician can tune his instrument by listening to this tuning fork in complete silence, in the same way, I will show you in a moment, we can capture this weak molecular signal under the conditions of complete darkness, in the absence of the noisy excitation. And how this happens shows actually this small animation. We hit the molecules of, in this particular case, of human blood plasma in a thin cuvette, bring the molecules vibrational modes into an excited state, and they vibrate and radiate infrared signals in the wake of the excitation. The excitation is gone. It was very short. This was the hammer that we applied to the tuning fork, right? And after the excitation, we have this weak molecular signal, which I actually have blown up here. It's basically roughly a factor of 100 times weaker than the excitation. But yet, with the newly developed solid-state attosecond metrology, very compact devices, we can capture the oscillating electric fields of these signals that are coming from the molecules. These are, if you like, the sounds of the molecules. But these are no acoustic waves, but these are infrared waves, oscillating a billion times faster than the acoustic waves. But I think the analogy is nevertheless helpful. This fingerprint signal is expected to change whenever a health-disease transition changes the sample's molecular composition, which we meanwhile verified for several chronic conditions, such as cancer, as well as, in collaboration with Professor Merkel's team, for coronary heart disease, and also for prediabetes and diabetes meanwhile. As a prominent example, I'd like to address lung cancer. Why exactly lung cancer? Well, every year, more than 1 million people on this planet are confronted with the deadly diagnosis, stage 4 lung cancer, where the remaining lifetime hardly exceeds 1 year, if at all. Could the disease be captured at an earlier stage before metastasis, the prognosis would definitely be much more favorable. There is an unmet medical need for a cost-effective and reliable, ideally blood-based, that's always the simplest test, a blood-based test that could serve as a basis for populational screening. Some 7 years ago, Michaela and her team initiated a collaboration with the Clinic of Pulmonology at the University of Munich. And in the framework of this collaboration, actually the clinical team set up and headed by Michaela started collecting samples from patients with different stages of non-small cell lung carcinoma, as well as samples from reference individuals who were either healthy, non-symptomatic healthy individuals, or carried some other disease, contracted some other disease of the same organ, like COPD or benign hematoma. What I'm going to show you here, the results from 470 samples of lung cancer patients and the same number of samples of reference individuals free from cancer, briefly controls, with the two cohorts carefully matched regarding the distribution of the subject's age and some other parameters, which all may and actually do change the molecular fingerprint of their blood samples. So it's very, very important that the two cohorts are matched to each other with respect to each other in order to avoid being fooled and saying hurrah, hurrah, if we see some difference between the two, between the signals from the two cohorts and assign it to lung cancer, but actually it is not due to lung cancer, but due to some differences in maybe the age or sort of other parameter or distribution of other parameters between the two cohorts. These are here what you see up there, the electric field molecular fingerprints of all selected samples. On this scale, actually, no differences between case and control fingerprints are well discernible or discernible at all. But if we zoom in on time interval, something like 1,000 femtoseconds behind the excitation, where definitely the molecular emission dominates the overall signal, because the excitation is gone there, right? So we are there already in the window of complete darkness, like the musician in the complete silence, right? We are there in the complete darkness, and there we can be pretty sure that the signal that we measure comes just from the molecules, and we see with great pleasure that the signals from the two different groups, the red traces are infrared electric field molecular fingerprints of cancer patients, and the blue traces are from the control subjects, that they are obviously significantly different. The magnitude of these differences can be best analyzed in the spectral domain, and here you see how the differences average out between all case and control samples in the spectral domain as a function of the 4 TNM stages for lung cancer. It is most reassuring that the magnitude of the differential infrared signal, which you see here as a function of wave number, that this magnitude grows, very distinctly grows with progression of the disease, suggesting that these molecular signals are indeed due to the disease rather than some other conditions. Let's now go back to the time domain. The differences between the case and control traces, and of course we can analyze these differences in the entire signal. I just zoomed into a small section that we have a good resolution, but you should imagine that this signal is going on way down to downtown Szeged, right? Something like that, right? So many other additional oscillations, right? We just zoomed in just to give you a feeling for how different the signals are. The actual analysis, of course, considers the entire signal. So these differences between the case and control traces can be used to distinguish the sample of a cancer patient from that of a healthy individual. And that's the goal of the game, right? And this is actually a task that artificial intelligence can do already today much, much better than even the most superior human intelligence. So this is the sort of obvious kind of textbook example for what is artificial intelligence good for, right? To recognizing these differences. Of course, before it can do so, it has to be trained. So a fraction of these traces, we just separate these traces into two groups. We take one group of the traces for training the algorithm and teaching the artificial intelligence, hey, if the signal looks like this, this is a healthy patient. Hey, if the signal looks like this, this is someone who carries stage 2 lung cancer in his or her body. And do this as many times as possible. To the bigger the cohort, the better. The better we can train the algorithm. I will show this to you in a moment. So just imagine we take 90%, to train the algorithm as good as possible, we take 90% of all the samples from both the case and the control cohorts for doing this job, training the algorithm, and retaining 10% for testing the trained algorithm. The algorithm is trained, we then take the 10% test samples, which the algorithm didn't see before. So these are independent samples, and the algorithm has to say, is this cancer or no cancer, right? And this is basically how we then assess the actual detection efficiency of the algorithm. This is the way. When training the algorithm, there is a parameter that we can freely adjust, the so-called discrimination threshold, which separates positive from negative cases to be predicted by the algorithm. To understand the basic concept of classification, let's consider, instead of of our multi-parametric fingerprint a one-dimensional health parameter. For instance, just a concentration of a simply individual biomarker, which standard laboratory medicine can measure these days. Just let's pick one biomarker, and basically this is what we refer to here generally as a health parameter. And just imagine that on the horizontal axis we just show here the concentration of this biomarker, and the two curves show the distribution for persons having contracted the disease that this biomarker is supposed to actually indicate. And the blue is the one, basically the distribution of the concentration of this biomarker for sort of true negatives for reference individuals. That's whom we refer to as controls. The discrimination threshold. This is the discrimination threshold, this vertical dashed line. The discrimination threshold determines what we call the true positive rate. And the true positive rate is the ratio of predicted positive, this is the shaded area, to true positive, which is the entire area under this distribution. This is the true positive rate. The discrimination threshold also determines the false positive rate, which is the ratio of the predicted positive to true negative. By varying this discrimination threshold, that's what we are doing in a moment, the false positive rate is traded off against the true positive rate, which is called sensitivity in the language of clinical science. The area under the curve, the so-called ROC, receiver operating characteristic curve, briefly AUC, is a measure for classification performance. For binary classification, EUC 0.5 is just pure chance, just toss a coin. EUC 1 is perfectness. So the reality is, of course, always in between. Approved biomarkers typically range between 0.7 and 0.9. This area under this red curve on the right-hand side. By varying this discrimination threshold, we can evaluate the AUC value of our lung cancer classifier, trained with the electric field molecular fingerprints for detecting non-small cell lung cancer at different stages, and here you see the results. The AUC values reaches hardly 60% for stage 1, which is, of course, gives room for quite a bit of improvement to be very moderate. But gets close already to 80% for stage 2 and even exceeds 80% for stage 3A, each of which are resectable non-metastasized stages with good prognosis. These values are encouraging but offer quite some room for improvement. How to get better? One option is to improve the infrared molecular fingerprinting technology, and we are working on that. The next generation instrument will offer a twofold improvement in spectral coverage, so basically a larger fraction of our fingerprint will become measurable, and about a 100-fold improvement in sensitivity. So basically more smaller changes in molecular concentrations in the blood sample will become discernible. These advances are certainly expected to allow the fingerprint picking up more cancer-specific signals with higher sensitivity, which may lead to a better separation of the case and control distributions in the multidimensional space of infrared fingerprint variables. But there are other options for advances. Even for the current sensitivity and specificity of the fingerprinting technology, better classification efficiencies could be achieved by simply using larger case and control cohorts. Logically, if we have more samples to train the algorithm with, we will have a better statistics. Basically, statistical noise will be automatically reduced. So what you see on this view graph is no physics, it's no biology, pure statistics. If we would just increase the cohort size from the roughly few hundred cases controls, which are depicted by the dots, these are the real experimental points, then we just continue right this curve. As you see, for relatively early stages, basically resectable stages 1, 2, 3A, up to close to 90%. But there is yet another even more powerful option, by reducing the spread of controls. By reducing the spread of controls. Again, simple statistics. All of a sudden, the area under the curve goes up. We can better separate between positives from negatives just because the two distributions are better separatable, right? So we should just try to decrease the spread of controls. How could this be done? By replacing the set of control fingerprints collected from other individuals by a set of fingerprints collected from the same person before contracting the disease. Collecting the reference fingerprints from the same person. A study initiated by Michaela revealed that this is not pure fiction. On the right-hand side, in a moment, you see the spread of blood plasma-based infrared fingerprints of healthy individuals on a two-dimensional principal component chart. So just imagine we extracted just two parameters of this multidimensional fingerprint to make it kind of, to visualize it for you, the main differences, just in 2 dimensions. These are basically the 2 parameters on the x and the y axis, and you see that these all healthy individuals have distinctly different infrared fingerprints. So the name fingerprint is allowed, right? Just as our real fingerprints are different, our infrared fingerprints are also distinctly different. Now let's see how those individual fingerprints spread as they are collected repeatedly. As they are collected repeatedly from the same person over a period of several weeks. Over a period of several weeks. As compared to the between-person variability, which is indicated by this big circle there. Well, I mean, the fingerprints of these healthy individuals spread over this whole area within the circle, right? The within-person, intrapersonal variability is much smaller. The within-person, intrapersonal variation over time is reduced by approximately a factor of 2.5. This strongly reduced spread is preserved, as it was shown in the original studies, preserved for even 6 months, and meanwhile, Tarek Issa and Michaela and co have also shown that actually it's preserved even over a period of 3 years. I'm not showing those data here, but you should just believe that for a few individuals we took blood samples even 3 years later, and they were still more or less within their own small island of individualized, personalized infrared fingerprint. As a consequence, if we could follow up individuals with a regular blood draw, we could collect a set of individualized fingerprints that could serve as controls in case this person contracts a disease some later time during his or her life. Now let's go back and see what would be the consequence. Here, the blue lines are fingerprints from different individuals, control fingerprints from different individuals. Now we know that the variation of the fingerprint of the same individual is varying, the size of that variation is by a factor of 2.5 smaller. So Cosmas Kapasides and his colleagues have been able to simulate this. And then basically the reference fingerprints look like this. The case fingerprints we left the same. These are really measured cancerous fingerprints, the red ones. No change. We just changed the control fingerprints to have a narrower distribution to simulate the case. What if the control fingerprints would have taken from you, right, just years before? Years before you have contracted this very disease. And having now one of those red lines, because you have contracted the disease, right? So you have now one of those red lines. This is your current fingerprint. So we can now ask the question how the algorithm would be able to separate this red line from these blue ones. My own fingerprints just taken year before. Easy job for great experts like Cosmas and co. And this is the result. Amazing, isn't it? With the current technology, stage 1, stage 2 lung cancer, in this very setting of self-referencing, could be captured with an AUC beyond 90%. There is no biomarker even inside that would get close to that. No biomarker for lung cancer, I mean. Stage 1, stage 2. Therefore, we conclude that longitudinal follow-up of individuals is the way to go. Is the way to go. And that's exactly what we do in the framework of our Health for Hungary program, which we initiated 2021 for following up 15,000 individuals. They donate, how much time do I have, Michaela? Probably it's over, right? Yeah, more or less. I'm just a couple of more minutes, I'm getting close. They donated and donate several blood samples during the first year of participation for allowing us to determine their personalized baselines, and one sample per year afterwards to monitor their health trajectories. Wow, I don't even need that. Great. This could serve as a basis for a cost-effective, risk-free populational screening for the 4 major non-communicable diseases, which could save both lives as well as resources of healthcare. Dear Minister, it can save resources. Dear Ministers, yes, it can save resources. Huge resources on the long run. And boost prosperity by extending the healthy life year of the population. This is a message to Minister Márton Nagy. Perhaps you can convey it to him. A preliminary result from the evaluation of infrared fingerprints of the first 4 samplings of more than 200 H4H Health for Hungary study participants confirms the finding of our previous pilot study. Just look at this, right? We have done what Michaela did with her team a few years ago on 30 individuals. Now we have data evaluated from 2,000 individuals, and you see. Again, we see this approximately factor of 2.5. It's actually different at different wave numbers, but believe me, if we average out over all these wave numbers, we get again this magic factor 2.5. Reduction in the spread of the healthy person's fingerprint. Blue versus red. Factor 2.5. This is the magic number, and we are the first in the world who figured out this number. Initially, none of the participants is supposed to have any one of these severe non-communicable diseases that are listed here. But during the 10-year study period, we expect more than, dear Bela, dear Professor Merkel, we expect more than 1,500 cardiovascular events. More than 800 participants will be diagnosed with diabetes. More than 500 will be diagnosed with COPD, and more than 160 with lung cancer. The samples of participants who do not contract, the lucky ones, and of course most of them will be in this category, fortunately, who do not contract any of these conditions will serve for establishing the populational reference range for infrared electric field molecular fingerprints, determining their individualized normal ages, so personalized medicine. Personalized medicine will start with these individualized infrared fingerprints, and assessing their dependence on covariates like your age, your sex, your body mass index, your smoking status, and other covariates that may affect your health parameters, including your infrared fingerprints. The fingerprints of participants with the newly diagnosed non-communicable diseases that I just listed you before, basically those something like altogether almost 3,000, right? 2,500 to 3,000 persons. Those fingerprints will be most valuable for scientific purposes because they will allow us to verify the capacity of infrared electric field molecular fingerprinting to detect common NCDs at their early stage. And how early we will be able to measure that because we sample the individuals frequently enough, unlike most other studies of this kind currently underway in the whole world. There are many longitudinal studies, but most of them are much less frequent. Recall participants typically every 3 to 5 years. We recall them each and every year to be able to eventually evaluate sharply how early we can possibly detect one of these major killers for mankind. Why would this be important? Well, every year 17 million people under the age of 70 die of one of these diseases. 17 million on Earth, and of course, many thousands in Hungary out of those 70 millions. 86% of them actually in low and middle income countries. Resulting in a dramatically reduced healthy life expectancy. So this is the average number of life years over which a person in a certain country, living in one of these countries, can enjoy good health. And I think this distribution is almost self-explanatory, and to me it was shocking. To me it was really shocking. More than 3.5 billion people are confronted with a perspective of living a healthy life some 15 to 20 years shorter than people being lucky enough to be born, grew up and live in a wealthy, well-developed country. 15 to 20 years. Just imagine. You become adult and will be confronted with this situation. You become adult in one of those countries here in this region between 0 and $10,000 GDP per capita. And you learn that your possible friends in maybe France, Germany, South Korea, Japan, even to some extent in Hungary, they didn't do anything else than you. They just were lucky enough that they have a perspective of living a healthy life 15 to 20 years longer. Do the low and middle income countries have any chance for catching up? Probably not. Probably not until being so dramatically inferior in terms of healthy life years of their citizens. Minister Martin Neut, if he would be here, who could explain us what this means for an economy if people just die away when they are best performance at an age of 50, 55 or 60, right? Just imagine that, what this means to an economy. These countries will never have a chance to catch up. On the contrary, the gap will be growing as long as we cannot do something on their health status. So, I guess the question everyone can answer for himself: if a peaceful, prosperous future of our planet is feasible with such a dramatic gradient between the two halves. I think it's unlikely. So what to do? Well, most of the premature deaths would be preventable by early intervention, triggered by early detection, urging the quest for affordable health monitoring. For that, we need to find the most economically viable set of health data. And here is the first grand question. As you see, it's formulated as a question. The most economically viable set of health data that enables comprehensive and dependable monitoring of human health. And as important is the scientific part of this, comprehensive and dependable monitoring, to assure that this is the scientific part of the challenge, but the technological part of the challenge is to make it economically viable, to make it cheap enough, to make it cost effective, equally important. Otherwise it will stay academic research. And it's wasted money and time to do that. We need to work simultaneously on making it economically viable. So that's why this is the right question. This is the right question. One of the reasons why I respect Professor Ernie Rubik so much. He put it so nicely in his book. One of the most difficult things in life, and particularly in science, I think is particularly true, is to find the right question. I think this is the right question. Which directly leads us to the next question. Can this set of data be acquired by molecular fingerprinting of human blood to provide sufficient information for health screening, at least for most prevalent non-communicable diseases? Our quest for the answer is driven by a vision which was beautifully formulated by Michaela. Imagine a tool that could catch issues before they become significant problems, like a sensitive radar, but one that is affordable to everyone and is fast and easy to use, to detect irregularities well before individuals get symptoms or would even think about seeing a doctor, to nip potential health hiccups in the bud, promising help to keep us on the road of well-being. Thank you for your attention. Thank you. Thank you.